When you flip a switch, the lights just come on. It's easy to picture electricity as an unstoppable wave, rushing instantly and effortlessly from the power plant straight to your wall outlet. But the universe doesn't give away energy for free. As those electrons travel through a wire, the material itself pushes back. We call this built-in pushback electrical friction, or more officially, resistance. Think of the voltage pushing those electrons like a high-pressure river. The current is the sheer volume of water rushing past. But the wire they travel through is a canyon filled with boulders and narrow bottlenecks. The size of that rocky channel physically limits how much water can actually get through at any given time. In a circuit, the conductive wire restricts the moving electrons in exactly the same way. Because energy never moves without effort, resistance serves as the hidden governor of the circuit, ensuring that electricity remains a predictable tool rather than a runaway force. So what exactly creates this electrical friction? In a physical wire, a material's exact shape and size dictate its baseline level of resistance. A long, thin wire has more obstacles, driving resistance up. A short, wide wire gives electrons room, dropping resistance down. Heat makes metal atoms vibrate, bumping into traveling electrons and pushing resistance even higher. In the early 19th century, George Simon Ohm discovered that this electrical friction followed exact, repeating mathematical patterns. Because these physical properties follow strict mathematical rules, engineers can design circuits with exact dimensions to dial in the precise amount of friction needed for any pathway. This chart shows Ohm's law, demonstrating the proportional relationship between voltage, current, and resistance. The straight, constant slope means if voltage stays the same, raising resistance guarantees the current will drop to a safer level. But physics demands a toll for this transaction. As the current fights its way through this electrical friction, the electrons lose some of their kinetic energy. That energy doesn't just disappear. Because energy can't be destroyed, the kinetic effort spent fighting through the wire transforms directly into thermal energy. Every single time electricity does work by pushing through a resistor, it leaves a thermal footprint behind. Heat is the unavoidable physical byproduct of electrical motion. We can see the true value of resistance by looking at its extreme limits. If you physically break a wire, you create an open circuit. The resistance becomes effectively infinite and zero current flows. But the opposite extreme is much more dangerous. If electricity finds a path where the resistance drops to near zero, it creates what engineers call a short circuit. Without resistance acting as a brake, the current surges violently. The electrons rush through the system so fast that the resulting friction generates extreme heat, rapidly melting the materials and destroying the equipment. This thermal destruction highlights why resistance is a vital safety boundary, acting as the structural brake that keeps power grids stable. The real engineering magic happens when we find the middle ground, using precise amounts of resistance to intentionally capture that byproduct of heat and make it do useful work. There is no better historical example of this than forcing current through a highly resistive, tightly coiled wire to generate heat so intense that it emits a brilliant visible light. The filament inside an incandescent bulb is a masterfully controlled bottleneck. The exact calculation of its resistance prevents the metal from instantly vaporizing, while maximizing the glow it produces. The ability to calculate and apply this pushback allows us to safely channel immense power into delicate electronics, transforming a raw physical phenomenon into a precise, global tool.